So, good day, everyone. So, we are the group 3 and we're going to discuss about the BGT AC analysis. So, I am Aline Morcilia Tungo together with my group mates Romero Apoloneo, Spencer So, Michelle Oy, and Miles Faith Valenzuela. So, BGT AC analysis has different types of configuration. So, namely fixed bias configuration, emitter bias configuration, the voltage divider bias configuration, the collector feedback configuration, the emitter follower configuration, and lastly, the common base configuration. But in our group, we focus on fixed bias configuration. So here's our circuit. VCC is equal to 10 volts. The RB is equal to 540 kilo ohms. The RC is 6 kilo ohms. The capacitor 1 is equal to 10 microfarad. And the capacitor 2 is equal to 10 microfarad also. The beta is equal to 100 and the output resistor is equal to 30 kilo ohms. So now we're going to proceed to the small signal equivalent model to be discussed by Michelle Oy.
The VC was lost according to a small signal analysis. All the DC sources should be turning off. That's why it became grounded and the RB and RC was disconnected. The C1 and C2 becomes a short circuit. That's why they lost in the equivalent model. Not also the C1 and C2, but also some few other voltages sources like V1, Vi and Vo because they bypass when the BC source was turning off and also when the capacitors were shortened and the rest was then made into a small signal equivalent model. Next was Miles Valenzuela.
In our case, we only have to focus on the three equations, which are the input impedance, output impedance, and the voltage gain as shown in the picture. Zi is gained by finding the value of the parallel of RB and beta Re. In the same way, Vo is found by finding the value of the parallel of RC and Ro. It is because impedance is simply the ratio of the voltage and current, whether it is input or output. That means it is the combined resistance of a circuit in a particular node. And since both resistors are parallel to each other, we use the parallel circuit formula to find the total resistance. As for voltage gain, it is simply the ratio of output voltage and input voltage. That is V out over Vn. However, we use the values of Rc, Ro, and Re instead since we are assuming all voltage sources are off. We use Re in the denominator because it is the general value used for theoretical solutions without considering factors such as temperature. That would be 26 megavolts over IE for the value of Re. As for the numerator, the ideal situation is that Ro would have the value of infinity, hence only using Rc. However, in the case that the exact value is applied, the value of the parallel of Rc and Ro would be the numerator. As such, this is why the formula is as such.
As for the solution for the circuit, I will be the one discussing it, and I'll show it in the form of a video. I hope you watch it.
Hello everyone, my name is Apollo Romero and I will be the one doing the solution for this circuit to find the input impedance, the output impedance, and of course the voltage gain for the amplifier. Let's start, shall we? First off, course, what we're trying to find is these three values: Zi, Zo, and Av. Now, first off, what should we expect? What should be the results? Expected results. See here, the input voltage should be like this, because of course, since we're using AC analysis, it should be a sine wave. Now we got the positive wave and a negative wave, but in the voltage output, we have the negative wave and the positive. It's reversed basically, and as you can tell, it becomes taller. Well, of course, what else would an amplifier do but to amplify the voltage? Now, now that we know what results to expect, how about we go through the key formulas? These three are the only the formulas that we need. Not the only formulas, but the formulas we need to find the three values. Then that's it. See, there's RB, the beta RE, RC, RE and RO will be discussed later. RO is this here, 30 kilo ohms. But usually, in a general term, we don't use 30 kilo. We don't use the actual value, but instead we use the infinity as the value for RO. And for RE, it is not from the outside. It's not inherently in a circuit, but inside a transistor instead. See, what if we remodel this circuit right here? What will happen? Here, if you try to look between the two of them, it's pretty different. See, but the greatest difference is that in here, the voltage DC is now gone. It's because in AC analysis, small signal analysis, we must assume that DC voltage, not a DC source, is 0. Because of that, that means it's an open circuit. So because of this right here, once VCC is gone, it grounds this part here and this part here. Hence, why in this new model, it's like this. Usually, this circuit, a circuit like this, is bigger. There are actually more components for this. There's actually another capacitor during at this wire here, but that's not important right now, because in this analysis, small signal analysis, what we're trying to focus on is this entire circuit. Now that we know what we're dealing with, we are going to move on to the actual solutions. First off, Zi, the input impedance. Okay. First off, RE. What's that? Well, usually, in a general term, RE is just 26 millivolts over IE. Now, this 26 millivolts in real-world application, it can change depending on certain factors. But since this is more of an ideal situation, ideal factors, the temperatures are just not considered for this. Therefore, it just stays in 26 millivolts. For this one, since we don't know IE, if we go over to our previous lesson, which is DC biasing, we get this formula for IE, which is beta plus 1 over times IB. And since we don't know what the value of IB is, we're going to use the formula of IB again. Of course, it's also in the previous lesson. for for the BGT biasing. IB is equals to VCC minus VBE over RB. Now, let's find IB first. Now, of course, we just substitute the values for VCC and RB, which can be found in our circuit right here. Which is 10 volts and 540 kilograms. No, not kilograms. 540 kilo ohm. And for the VBE, as you might remember, VBE is the voltage drop, which is usually 0.7. And if we solve this, it'll turn out into 17.22 microamperes or microamps. Whatever floats your boat. Next would be finding the IE. Now it's, of course, it's simple. Again, it's a simple formula. We just add beta plus 1 and then times it to 17.2 microamps, which is the IB. And we get 1.74 milliamps. And now for RE, as you remember, RE is 26 millivolts over IE. We do that, and then we get 19.94 ohms. Now, Now we will find the input impedance. Here, see here. RB and BRE. If you remember, this formula basically equates to this formula right here: RB BRE over RB plus BRE, beta RE. Sorry, is equals to this. We just substitute the values: 540, 100, 14.94. That is, and then we get 1.489 kilo ohms. That is our input impedance. Now that we know what's our now we got the input impedance, let's go to output impedance. Now, this is where I'll tell you. This is where I remind you again that in a general sense, RO is usually not the actual value, but instead we replace it with the value of infinity. Because of that, we really cannot, since it is infinity, we cannot put the actual value. So we instead remove RO from the equation. Now we only get RC for the ZO, or output impedance. Because of that, we just substitute RC for ZO, which is 6 kilo ohms. Now, that's basically it. You just have to follow the formula, and you have it. Now for the voltage gain, and this is where we'll be able to find out if the expected results would be like right here. Still simple, AV, since we don't have RO because it's now infinity, we only have RC over RE. As you might remember, RE is 14.94 ohms, so we just do 6 kilo ohms over 14.94 ohms. Reminder, there is a negative sign there, so that means that your answer should be negative as well, except if except if there's another negative sign there, denominator. Both of the numerator and the denominator are negative. opposite instead. Now you look at this is the voltage gain right after the amplifier. Now what do you notice? It's a negative voltage gain, which should be what we expected for this one. As you see in the voltage output, the voltage gain is at negatives. The wave is at the negatives. Now this is only for the first few seconds. If it was any further, then it would have been positive instead. Now we got all of that. We finally got the ZI, ZO, and AB. What if we change RO into the actual value now, which is 30 kilo ohms? Here we have 30 kilo ohms. It's just business as usual. We do the same thing here for IB. To remember, just do RC RO over RC plus RO. Substitute the values 6 kilo ohms and 30 kilo ohms, and we get 5 kilo ohms. And then for AV, just replace the numerator with ZO, or substitute the values again, and we get negative 334.67 for the voltage gain. Yep, that's how we solve it. Now, I know it's a bit disappointing that there's not a lot of it, there's not a lot of solving, but that is to be expected because this is, of course, a fixed bias configuration. It is the simplest model you could use for small signal AC analysis. So that's why it has only a little bit of solving, just a little bit of doing. It's not that hard. The only thing hard is trying to find a calculator to do any of this. And that's the solution. Basically, if your RO is infinity, which is generally what it is, our ZO is 6 kilo ohms, our AV is negative 401.61, but if we change our RO to the actual value of 30 kilo ohms, our ZO is 5 kilo ohms, and our AV is negative 334.67. And regardless of the RO, our ZI would be 1.229 kilo ohms. So that's it. I hope you learned something in this solution. It's not that hard. I hope you understood. And thank you for listening.
Hi, I'm Spencer Diso, and my job is to verify and simulate the values on the circuit. So the first step is to open the Proteus and find the devices needed for the simulation. The devices that we need are generic resistor, polarized capacitor, and a silicon NPN, which the code is BC107, which can be found in the component mode. So the first thing is to put the V sign, which can be found in the generators. Then we put the capacitor and then the transistor. So you can see the base, the collector, and the emitter of the transistor. Next is we put the first resistor and then the second resistor, together with the AC ammeters to measure the current flowing across the resistors. and then we put another capacitor here. And don't forget the terminals, which is the ground. Next is to put above a V sign, and we must put another AC ammeter here to measure the current. We just have to move this above and this above. The value for the first resistor is 540K and 6K for the second resistor. And let us change also the value of V signs into 10 volts. And last is to put a voltage probe to measure the voltage. Let's change the display range of each ammeters so that we can see the values as we run the simulation. And as you can see, these are the values that we get by running the simulation. That's all for my part.
So that's all for the Group 3's presentation. Thank you for listening and God bless.